0, or 1, 2, 3, 4, and then all of a sudden, all of your thermostats, all of your smart thermostats in the building are now attacking some computer at the Pentagon, right? So sometimes you can see actually a fairly large spike in traffic. But what happens if you get both at the same time? You might not be able to see it. So what we wanted to do is figure out in real time, and I mean, or near real time, but we're talking a latency period of less than a second. Can you tell if the pattern of reporting of your sensors has changed from what is typical for that state, right? So we did a probabilistic framework. So Karim started playing with latent Dirichlet allocations and distributions to be able to figure out, first off, what the different states, are there different states of behavior that we're seeing in the building? And then for the given state that we've detected, is this a likely or unlikely pattern of data to see, right? So if we have an unlikely pattern, it can suddenly be like, wait a sec, this doesn't make sense. If we're in cooling, this is not the way that the data should be shaped. Something is going on, and we can investigate right away, and it can throw up an alarm. The next step of this research is actually to feed it into a Bayesian network. So we're preparing a journal article now that actually takes these states and actually uses them as inputs for Bayesian networks. So we can actually do a much broader kind of root cause detection down to the sensor device of what's causing the issues. So we're looking for data traffic anomalies, because if you don't have good data streams, you don't have a smart building, unfortunately. And here, it's not as aggressive as the first paper. We're limiting ourselves to 2 months of data. There is no labeling, so everything's unsupervised, and this is working entirely on the edge, right? So Dirichlet is some pretty scary math, but basically in a short form, you're trying to figure out what the different probabilities are. So it's a beta distribution looking at the different probabilities for different states, what your likelihood of data following a particular pattern is, right? And then, so that's the distribution, and then the allocation is a joint probability distribution for all of the variables. So given a system K, a day D, so answering that previous question of does day of the week matter? Yes, it matters. And then what record it is on that day, and then for what state. So is it like a heating state, a cooling state, a shoulder season state? What's the likelihood that the data would actually follow the shape that we have? So let me just show you a little bit about the system we have set up. So we're very, very fortunate that our president, back when he was the provost, approved an extra technical package for one of the newer buildings on our campus. So we have 14,000 building automation system data points. I would say about 13,800 are typical, but we do have an extra couple hundred of like branch BTU meters, airflow monitoring stations. We have a little bit more monitoring than typical. The most important thing was one line that we put in the controls contract, was that the controls contractor was required to send tuples that were the full context point ID, so network controller, field controller, point name, the timestamp, and the value at every change of value above a threshold. So I have 14,000 data points streaming at every change of value since this building opened in 2019. So I have about a 5 billion point data set. I wish I could share it, I really do. I'm gonna try and find out ways of being able to share small, non-contextualized pieces of it to make it actually more useful. So we have a streaming edge device. The way that we've gotten around this, if you're ever trying to negotiate with your own organization to get access to your data, we have rented 2 virtual machines from our central computing system. One is on the mission critical network, and all it does is it copies every piece of data that gets communicated to that head end. So that's how we're stealing. We're basically cloning the data. It sends it to a second device that is on our campus, like behind our campus firewall. And it's a one-way outbound only VPN. So nothing can go in. It can't be hacked. And then we have a 2-way VPN to our own private cloud where we're actually storing the data. So this way we can reconfigure the gateway remotely, but you basically can't get into the mission critical system. So this is how we navigated that data streaming. So we're looking at the data exploration. We've got a few different building systems in terms of how we've grouped things. So the BTU meters, these are the branch meters we have on every floor. So this is telling us on our heating and cooling systems, basically our MCP delta T. So our sensible heating or cooling load as it's flowing through at these different areas. We have our electricity meters, and this is basically for lighting and power consumption. We have room HVAC systems, and they're either on the academic side or the resident side. This is a 9-story academic building with a 20-story residential tower on top. We have a hot water system. Again, we distinguish between academic and residential because they're just very different, obviously, in terms of performance. We have our airflow. We have our VAV boxes, our chilled water systems, our lab HVAC systems. We do have a number of commercial or like scientific labs. So Phoenix air valves and very specific lab equipment. Miscellaneous, which we just had no way of other distinguishing, and then we have active chilled beams as well. All right. And then we have another thing with kind of a low streaming rates, and then we have the ERVs. Those are the energy recovery ventilators. They basically serve as the air handling units. So these are how our average daily counts are. You can see significant numbers in some systems, less significant in others. If you actually look at it more visually, you can see over the course of the year how things change. And then so the weekly system recording performance, you can actually start to get a sense on a weekly basis, how does this look over the course of the year? What really comes out is if you actually start to plot the state, right? So the LDA actually looked at it and realized, or pulled out to us that there were 3 different states. One of them is obviously the heating state, that's our state 2, because you can see it's got a lot more BTUs. Another one is the cooling state, because you can actually see more of the chilled water system, you can see a lot of the energy meters, you can see a lot more room-based system responses. And then the top is a little bit more balanced, that's our shoulder season. And if we just look at it, we keep that graph on the right-hand side in mind, you can actually see the same thing. So in the summertime, you can see state 1, the data's peaking. State 2, so we have a high probability of state 1 in the summer, high probability of state 2 in the winter, which unfortunately in Canada for us is from September until about April. And then we have these peaks in the shoulder season, and this is usually tied to the switchover. We have a 2-pipe system in our residence system. That means that it gets hot water in the winter, it gets cold water in the summertime, and then there's a period where the system flips from one to the next. So this is the theta distribution, and the model actually lets us predict what state we're in. Again, like we said, we're now using this as a input for a Bayesian network. Now, if we want to use this for results, we can actually start to take our real data and say, does this look like what we're expecting it to be? And you can see right here, you can see anomalies. We took a 2% threshold. So we said, you know, if we have 2% probability or less, it's anomalous data. Right, and that's pretty conservative. It could probably be a little bit higher. We could probably say 10% or less. We just wanted to minimize false alarms. But what's really interesting, if you look at the cluster of points at the far left, you can see it's very, very unlikely that we would have that thing. But if you actually look at that data stream, if you look at the sheer number of points, you would have no way of knowing that that's actually wrong, right? And when we actually looked at the data, and I'll show you what this shows in the next piece, you can see our main central air handling system actually was stopped reporting entirely. We had a period of several days where we had no data from that one system. But if you look at it in context, we have 14,000 points. We never figured out that we were missing that because there's only 22 points on that, and some of them are simple day-night occupancy sort of shifts. But as soon as you see here, you actually have the power to see down at the system level, or if we were willing to implement it further, and this is what the Bayesian network is going to inform, is if we find an issue here, then it can prompt a second set specifically for that subsystem, and then we can actually go down to the device. So we can say to facilities management, you have a sensor in this room that stopped communicating, which is going to mean the room's going to get too hot or too cold. If it's demand-controlled ventilation, you're not going to be ventilating it properly, et cetera. So it wound up being really important to actually keep track of that and communicate it properly to your facility manager so they actually know what to fix rather than just trying to generically fix everything. So, in conclusion, LDA is actually incredibly powerful as a tool, actually looking at the states and then at the proportions and the likelihood that the data is going to have a particular shape, right? So the net number of counts is a good first warning system, but being able to actually look at the distribution between systems actually makes this much more powerful in terms of starting to get root cause analysis of where you might have signal failures in your network. Like I said, this has still got nothing to do with the actual data itself in terms of like the values. So this isn't telling me that my sensor, like my thermostat is reading the wrong value. It's just telling my thermostat isn't communicating to my system. But that's always going to be a root cause of performance failures as well. So it can tell, we can get sensor outages, we can tell if we've missed things, we can detect cyber attacks if we suddenly had extremely high values on a system that don't make sense, or unexpected state transitions, right? If all of a sudden we're in the cooling season and it tells us that we're in a heating state, that tells us something very, very wrong, right? We should not be having a lot of noise on our heating system in the middle of July when it's 32 degrees Celsius outside. So next step is to integrate this into our anomaly detection systems and actually start to bring it into more of an automated fault detection and diagnosis system. So working with some of the other work that we have, some of the graph deviation network work that will be presented on the website, my student who couldn't make it. Again, this was funded by the Natural Science and Research Council of Canada, so this is kind of my foundational research grant, and happy to answer any questions.